Hi, everybody. So I'm Raymond. I'm not television's Raymond Blum that you may remember from The Facts of Life. I'm a different Raymond Blum. Private joke. Um, so I work in site reliability at Google in technical infrastructure storage, and we're here to make sure that things, well, we can't say that things don't break, that we can recover from them, because of course we all know things break. Specifically, we're in charge of making sure that, you know, when you hit send, it stays in your sent mail. When you get an email, it doesn't go away till you say it should go away. When you save something in Drive, it's really there, as we hope and expect forever. And I'm going to talk about some of the things that we do to make that happen, because the universe and Murphy and entropy all tell us that that's impossible. So it's a constant, never-ending battle to make sure things actually stick around. I'll let you read the bio. I'm not going to talk about that much. Common backup strategies that work maybe outside of Google really don't work here, because they typically scale effort with capacity and demand. So if you want twice as much data backed up, you need twice as much stuff to do it. Stuff being some product of time, energy, space, media, etc. So that maybe works great when you go from a terabyte to 2 terabytes, not when you go from an exabyte to 2 exabytes. And I'm going to talk about some of the things we've tried, and some of them have failed. That's what the scientific method is for, right? And then eventually we find the things that work. When our experiments agree with our expectations, we say, yes, this is what we will do. And the other things we discard. So I'll talk about some of the things we've discarded, and more importantly, some of the things we've learned and actually do. And there's a slide. Yes, solidifying the cloud. I worked very hard on that title, by the way. One thing that, well, let me go over the outline first, I guess. Really, we consider, and I personally obsess over this, is that it's much more important. You need a much higher bar for availability of data than you do for availability of access. Like, if a system is down for a minute, fine. Hit submit again on the browser and it's fine, and you probably blame your ISP anyway, not a big deal. On the other hand, if 1% of your data goes away, that's a disaster if it's not coming back. So really, durability and integrity of your data is our job one, and Google takes this very, very seriously. We have thousands of engineers. All right, we have many engineers, not thousands, dedicated to this. But really, every Google engineer understands this. All of our frameworks, things like Bigtable and formerly GFS, now Colossus, all are geared towards ensuring this. And there's lots of systems in place to check and correct any lapses in data availability or integrity. Another thing we'll talk about is redundancy, which people think makes stuff recoverable, but we'll see why it doesn't in a few slides from now. Another thing is MapReduce, both a blessing and a curse. A blessing that you can now run jobs on 30,000 machines at once. A curse that now you've got date files on 30,000 machines at once, and something's going to fail. So we'll talk about how we handle that. I'll talk about some of the things we've done to make the scaling of the backup resources not a linear function of the demand. So if you have 100 times the data, it should not take 100 times the effort to back it up. I'll talk about some of the things we've done to avoid that horrible linear slope. Restoring versus backing up. That's a long discussion we'll have in a little bit. And finally, we'll wrap up with a case study where Google dropped some data, but luckily my team at the time got it back. And we'll talk about that as well. So the first thing I want to talk about is what I said, like my personal obsession, in that you really need to guarantee the data is available 100% of the time. People talk about how many nines of availability they have for a front end. If I have 3 nines, 99.9% of uptime is good. 4 nines is great. 5 nines is fantastic. 7 nines is absurd. It's femtoseconds a year outage. That's just ridiculous. But with data, it really can't even be 100 minus epsilon, right? It has to be there 100%. And why? This pretty much says it all. If I lose 200, if I lose 200K of a 2 gigabyte file, well, that sounds great statistically. But if that's an executable, what's 200K worth of instructions, right? I'm sure the processor will find some other instruction to execute for that span of the executable. Likewise, these are my tax returns that the government's coming to look at tomorrow. those numbers couldn't have been very important. You know, some small slice of the file is gone. Like really, you need all of your data. That's the lesson we've learned. It's not the same as availability, front-end availability, where you can get over it. You really can't get over a data loss. A video garbled, that's the least of your problems, but it's still not good to have, right? So, yeah, we go for 100%, not even minus epsilon. So a common thing that people think, and that I thought, to be honest, when I first got to Google, was, well, we'll just make lots of copies. Okay, great. And that protects you. That actually is really effective against certain kinds of outages. For example, if an asteroid hits a data center and you've got a copy in another data center far away, unless that was a really, really great asteroid, you're covered. On the other hand, picture this. You've got a bug in your storage stack. Okay, but don't worry, your storage stack guarantees that all writes are copied to all other locations in milliseconds. Great, you now don't have one bad copy of your data, you have 5 bad copies of your data. So redundancy is far from being recoverable, right? It handles certain things. It gives you location isolation, but really there aren't as many asteroids as there are bugs in code or user errors. So it's not really what you want. Redundancy is good for a lot of things. It gives you locality of reference for I/O. Like if your only copy is in Oregon, but you have a front-end server somewhere in, I don't know, in Hong Kong, you don't want to have to go across the world to get the data every time. So redundancy is great for that, right? You can say, I want all references to my data to be something fairly local. Great, that's why you make lots of copies. But as I said, to say, I've got lots of copies of my data so I'm safe, you've got lots of copies of your mistaken deletes or, corrupt writes of a bad, buffer. So this is, not at all what redundancy protects you against. Let's see, what else can I say? Yes, when you have a massively parallel system, you've got, much more opportunity for loss. MapReduce, I think, rough show of hands. Who knows what I'm talking about when I say MapReduce? All right, that's above critical mass for me. It's a distributed processing framework that we use to run jobs on lots of machines at once. It's brilliant. It's my second favorite thing at Google after the omelet station in the mornings. And it's really fantastic. It lets you run a task, trivial effort. You can run a task on 30,000 machines at once. That's great until you have a bug, right? Because now you've got a bug that's running on 30,000 machines at once. So when you've got massively parallel systems like this, the redundancy and the replication really just makes your problems all the more horrendous. And you've got the same bugs waiting to crop up everywhere at once, and the effect is magnified incredibly. Local copies don't protect against site outages. So a common thing that people say is, well, I've got RAID, I'm safe. And another show of hands, RAID, anybody? Yeah, redundant array of inexpensive devices, right? Why put it on one disk when you put it on 3 disks? I once worked for someone who, it was really sad, he had a flood in his server room. So his machines are underwater, and he still said, but we're safe, we've got RAID. I thought, like, no, I'm sorry, my mom told me I can't talk to you. That's, sorry, yeah, it doesn't help you against local problems, right? Yes, local, if local means 1 cubic centimeter. Once it's a whole machine or a whole rack, I'm sorry, RAID was great for a lot of things, it's not protecting you from that. And we do things to avoid that. GFS is a great example. So the Google file system, which we used throughout all of Google till almost a year ago now, was fantastic. It takes the basic concept of RAID, use encoding to put it on n targets at once, and you only need n-1 of them, so you can lose something and get it back. Instead of disks, you're talking about cities or data centers. Don't write it to one data center. Write to 3 data centers, and you only need 2 of them to reconstruct it. That's the concept, and we've taken RAID up a level, or 5 levels maybe, so to speak. So we've got that, but again, redundancy isn't everything. One thing we found that works really, really well is, and people were surprised, I'll jump ahead a little bit. People were surprised in 2011 when we revealed that we use tape to back things up. People said, tape, that's so 1997, Tape is great because it's not disk. If we could, we'd use punch cards, like that guy in XKCD just said. Why? Because if you imagine this, you've got a bug in the prevalent device drivers used for SATA disks, right? Okay, fine. You know what? My tapes are not on a SATA disk, okay? I'm safe. My punch cards are safe from that, Okay, you want diversity from everything. If you're worried about site problems, locality, put it in multiple sites. If you're worried about user error, have levels of isolation from user interaction. If you want if you want protection from software bug, put it on different software. Different media implies different software. So we look for that. And actually what my team does is guarantee that all the data is isolated in every combination. Take the Cartesian product, in fact, of those factors. I want location isolation, isolation from application layer problems, isolation from storage layer problems, isolation from media failure, and we make sure that you are covered for all of those, which is not fun until, of course, you needed it. Then it's fantastic. So we look to provide all of those levels of isolation, or I should say isolation in each of those dimensions, not just location, which is what redundancy gives you. Telephone. Okay. This is actually it's a plain slide, but it's my favorite slide. I once worked at some place, named to be withheld, okay, because that would be unbecoming, where the people in charge of backups, there was some kind of failure, all the corporate data and a lot of the production data was gone. And they said, don't worry, we take a backup every Friday. They pop a tape in, it's empty. The guy's like, oh, well, I'll just go to the last week's backup. It's empty too. And he actually said, I always thought the backups ran kind of fast. And I also wondered why we never went to a second tape. It's like a backup is useless. It's a restore you care about. So one of the things we do is we run continuous restores. We take some sample of our backup, some percentage, random sampling of n%, then it depends on the system, usually it's like 5, and we just constantly select at random 5% of our backups and restore them and compare them. Why? We check something. We don't actually compare the original. Why? Because I want to find out that my backup was empty before I lost all the data next week. Okay? This is actually very rare, I found out. So we went to one of our tape drive vendors who was amazed that our drives come back with all this read time. Usually when they get them back, the drives log how much time they spent reading and writing. Most people don't actually read their tapes, they just write them. So, I'll let you project out what a disaster that is waiting to happen. I thought the tapes were, I always wondered why we never went to second tape. So we run continuous restores over some, sliding window, but 5% of the data to make sure we can actually restore it. And that catches a lot of problems, actually. We also run automatic comparisons. And it would be a bit burdensome to say, we read back all the data and compare to the original. That's silly, because the original has changed in the more than microseconds since you backed it up. So what we do is we actually checksum everything, compare it to the checksums, make sure it makes sense. Okay, we're willing to say that, checksum algorithms know what they're doing, and this is still the original data. But we actually get it back onto the source media to make sure it can make it all the way back to disk or to flash or wherever it came from initially to make sure it can make a round trip. And we do this all the time. And we expect there'll be some rate of failure, but we don't look at, a file did not restore in the first attempt. It's more like, the rate of failure on the first attempt is typically n. The rate of failure in the second attempt is typically y. Okay, if those rates change, something has gone wrong. Something's different, and we get alerted. But these things are running constantly in the background, and we know if something fails. And, luckily we find out before someone actually needed the data, right? We're testing restores before, because you only need the restore when you really need it. So we want to find out if it was bad before then and fix it. Bad segue, not a smooth segue, but I'll take it. One thing we have found that's really interesting is that, of course, things break, right? Everything in this world breaks. Second law of thermodynamics says that, and we can't fight it. But we do what we can to safeguard it. We have, who here thinks that tapes break more often than disk, or who thinks disk breaks more often than tape? Lifetime, well, it's not a fair comparison. But let's say mean time to failures, if they were constantly read and if they were constantly written and read at the same rates, which would break more often? Who says disk?
Are you talking about media or?
Media failure, yeah. Disk breaks all the time, but you know what? You know when it happens. So that's the thing. So you have RAID, for example. A disk breaks, you know what happened, you're monitoring it, fine. A tape was locked up in a warehouse somewhere. It's like a light bulb. People say, why do light bulbs break when you hit the switch and turn them on? That's stupid. It broke last week, but you didn't know until you turned it on. Okay? It's Schrodinger's breakage, right? It wasn't there until you saw it. So tapes actually last a long time. They last really well, but you didn't find out till you needed it. That's the lesson we've learned. So the answer is recall them and read them before you need it. Okay? Even given that, they do break. So we do something that, as far as I know, is fairly unique. We have RAID on tape, in effect. We have RAID 4 on tape. We don't write your data to 8 tape, because if you care about your data, it's too valuable to put on one tape and trust this one single point to failure. Because, they're cartridges. The robot might drop them. Some human might kick it across the parking lot. Magnetic fields, a neutrino may finally decide to interact with something. You have no idea. Okay? So we don't take a chance. When we write something to tape, we tell you, you know what, hold on to your source data until we say it's okay to delete it. Do not alter this. If you do, you've broken the contract. And who knows what will happen, okay? We build up some number of full tapes, typically 4, and then we generate a 5th tape, a code tape, by XORing everything together, and we generate a checksum. Okay, now you've got RAID 4 on tape. When we've got those 5 tapes, okay, that you could lose any one of, and we could reconstruct the data by XORing back, in effect, we now say, okay, you can change your source data. These tapes have made it to their final physical destination, and they are redundant. They are protected. Because if it wasn't worth that weight, it wasn't worth you to back up. It couldn't have been that important, really. So every bit of data at Google that's backed up gets subjected to this. And this gives you a fantastic increase. The chances of a tape failure, we probably lose hundreds a month. We don't have hundreds of data losses a month because of this. If you lose one tape, our system detects this through this continuous restore. It immediately recalls the sibling tapes, rebuilds another code tape, all as well. In the rare case, and I'm not saying it doesn't happen, in the rare case where 2 tapes in a set are broken, well, now you're kind of hosed. Only if the same spot on the 2 tapes was lost. So we do reconstruction at the subtape level. And we really don't have data loss because of these techniques. They're expensive, but that's the cost of doing business. Yeah, well, I talked about light bulbs already, didn't I? Okay. So let's switch gears and talk about backups versus, actually about backing up lots of things. I mentioned MapReduce. Not quite at the level of 30,000, but typically our jobs produce many, many files. The files are sharded. So you might have replicas in Tokyo, replicas in Oregon, and replicas in Brussels. Okay. And they don't have exactly the same data. They have data local to that environment. Users in that part of the world, requests that have been made referencing that, whatever. But the data is not redundant across all of them at first. So you have 2 choices. You can make a backup of each of them and then say, you know what, I know I've got a copy of every bit, and when I have to restore, I'll worry about how to consolidate it then. Okay, not a great move, because when will that happen? It could happen at 10 a.m. when you're well rested on a Tuesday afternoon and your inbox is empty. It could happen at 2:30 in the morning when you just got home from a party at midnight. Or it could happen on Memorial Day in the US, which is also, let's say, a bank holiday in Dublin. It's going to happen in the last one, right? So it's late at night. You're under pressure because you've lost a copy of your serving data and it's time to restore. Now let's figure out how to restore all this and consolidate it. Not a great idea. You should have done all your thinking back when you were doing the backup, when you had all the time in the world. And that's the philosophy we follow. We make the backups as complicated and take as long as we need. The restores have to be quick and automatic. I want my cat to be able to stumble over my keyboard, bump her head against the enter key and start a successful restore. And she's a pretty awesome cat. She can almost do that, actually. But not quite, but we're working on it. It's amazing what some electric shocks can do. But yeah, early on, we didn't have this balance, to be honest. And then I found this fantastic cookbook where it said, hey, make your backups quick and your restores complicated. And yes, that's a recipe for disaster. Lesson learned. We put all the stress on restores. Recovery should be stupid, fast, and simple. But the backups take too long. No, they don't. The restore is what I care about. Let the backup take forever. Okay? There are, of course, some situations that just doesn't work, and then you compromise with the world. But this carries the huge percentage of our systems work this way. The backups take as long as they take. The client services that are getting the data backup know this expectation and deal with it. And our guarantee is that the restores will happen quickly, painlessly, and hopefully without user problems. And I should, in a little while in the case study, I'll talk about what fast means. Fast doesn't necessarily mean microseconds in all cases, but relatively fast within reason. And yeah, as a rule, yes, when the situation calls for data recovery, think about it. You're under stress, right? Something's wrong. You've probably got somebody who is a much higher pay grade than you looking at you in some way. Not the time to sit there and formulate a plan. Okay, time to have the cat hit the button. Okay, and then we have an additional problem at Google, which is scale. So I'll confess, I used to lie a lot. I mean, I still may lie, but I don't, not in this regard. I used to teach, and I used to tell all of my students, this is, I guess, 8 years ago, 9 years ago, I used to tell them there was no such thing as a petabyte. That is like this hypothetical construct. It's a thought exercise. Then I came to Google, and in my first month, I had copied multi-petabyte files from one place to another. It's like, oh, who knew? So think about what this means. If you have, something measuring in gigabytes or terabytes, and it takes, a few hours to back up, no big deal. If you have 10 exabytes, gee, if that scales up linear, I'm going to spend 10 weeks backing up every day's data. Okay, in this world, that cannot work. Okay, linear time and all that. So yeah, we have to learn how to scale these things up. We've got a few choices. We've got dozens of data centers all around the globe. Okay, do you give near infinite backup capacity in every site? Do you cluster things so that all the backups in Europe happen here, all the ones in North America happen here, Asia and the Pacific Rim happen here? Okay, then you've got to write bandwidth considerations. How do I ship the data? Well, didn't I need that bandwidth for my serving traffic? Maybe it's more important to make money. So you've got a lot of considerations when you scale this way. And we had to look at the relative costs. And there are compromises. We don't have backup facilities in every site. But we've got this best fit, right? And it's a big problem in graph theory, right? In how do I balance the available capacity, on the network versus where it's cost effective to put backups, where I get the most bang for the buck in effect. And sometimes, we tell people, no, put your service here, not there. Why? Because you need this much data backed up, and we can't do it from there unless you're going to make a magical network for us. We've got a speed of light to worry about. So this kind of optimization, this kind of planning goes into our backup systems because it has to. Because when you've got, like I said, exabytes, there are real world constraints at this point that we have to think about. Stupid laws of physics. I hate them. Right. So, and then there's another interesting thing that comes into play, which is what do you scale? You can't just say, I want more network bandwidth and more tape drives. Okay, each of those tape drives breaks every once in a while. If I've got 10,000 times the number of drives, am I going to have 10,000 times the number of operators to go replace them? Do I have 10,000 times the amount of loading dock to put the tape drives on until the truck comes and picks them up? None of this can scale linear. It all has to do better than this. My third favorite thing in the world is this quote. I've never verified how accurate it is, but I love it anyway, which was some guy in the post-World War II era, I think it is, when America's starting to get into telephones and become one in every household. This guy makes a prediction that in N years time, in 5 years time, at our current rate of growth, we will employ 30% of the US population as telephone operators to handle the phone traffic. Brilliant, okay? What he, of course, didn't see coming was automated switching systems, right? This is the leap that we've had to take with regards to our backup systems. We can't have 100 times the operators standing by to, not phone operators, computer, hardware operators, standing by to replace bad tape drives, put tapes into slots. It doesn't scale, right? So we've automated everything we can. Scheduling is all automated. If you have a service at Google, you say, here's my data stores. I need a copy every N. I need the restores to happen within M. And systems internally, schedule the backups, check on them, run the restore testing that I mentioned earlier. You don't do this because it wouldn't scale. The restore testing, as I mentioned earlier, is happening continuously. Little funny demons are running it for you and alert you if there's a problem. Integrity checking, likewise, the checksum is being compared automatically. It's not like you come in every day and look at your backups to make sure they're okay. That would be kind of cute. When tapes break, I was on that. I've been involved in backups for 3 years. I don't know when a tape breaks. when a broken tape is detected, the system automatically looks up who the siblings are in the redundancy set I mentioned and described earlier. It recalls the siblings, it rebuilds the tape, sends the replacement tape back to its original location, marks tape X has been replaced by tape Y, and like at some point you can do a query, I wonder how many tapes broke. And if the rate of breakage changes, like we typically see 100 tapes a day broken, all of a sudden it's 300, then I would get alerted. But until then, why are you telling me about 100 tapes? Like it was the same as last week. Fine, that's how it is. But if the rate changes, you're interested, right? Because maybe you've just got a bunch of bad tape drives. Maybe, like I said, a neutrino acted up. We don't know what happened, but something is different. You probably want to know about it. Okay, but until then, it's automated. Steady state operations, humans should really not be involved. This is boring. Logistics, packing the drives up and shipping them off. Obviously, humans have to, at this point in time still, humans have to go and actually like remove it and put it in a box. But as far as like printing labels and getting RMA numbers, I'm not going to like ask some person to do that. That's silly. We have automated interfaces that get RMA numbers, that prepare shipping labels, look to make sure that drives that should have gone out, have in fact gone out, get acknowledgement of receipt. And if that breaks down, a person has to get involved. But if things are running normally, why are you telling me? Honestly, like this is not my concern. I have better things to think about. Library software maintenance, likewise. If we get if we get firmware updates, I'm not going to run an SD card into like those in the libraries. But that's crazy. Okay, download it, let it get pushed to a canary library, let it be tested, let the results be verified as accurate, then schedule upgrades in all the other libraries. I really don't want to be involved. This is normal operations. Please don't bother me. And this kind of automation is what lets us, in the time I've been here, our number of tape libraries and backup systems have gone up at least a full order of magnitude, and we don't have 10 or 100 times the people involved. Obviously, we have some number more, but it's far from a linear increase in resources. Yes, okay. So how do you do this, right? We have to do some things, as I say, that are highly parallelizable. Yes. We collect the source data from a lot of places. Okay, this is something that we have our Swiss Army knife, MapReduce. Okay, MapReduce is, like I said, it's my favorite, one of my favorites. When we say we've got files on all these machines, fine. Let a MapReduce go collect them all, okay, put them into a big funnel, spit out one cohesive copy, okay, and I will take that thing and work on it. Okay, if a machine breaks, because when you've got 30,000 machines, each one has a power supply, 4 hard disks, a network card, something's breaking every 28 seconds or so. Okay, so let MapReduce handle that, and its sister systems handle that. Don't tell me your machine died. One's dying twice a minute. That's crazy. Okay, let MapReduce and its cohorts find another machine, move the work over there, and keep hopping around until everything gets done. If there's a dependency like, oh, this file can't be written until this file is written, again, don't bother me. Schedule a wait. If something waits too long, by all means, let me know. But really, like, you handle your scheduling. This is an algorithm's job, not a human's. Okay? And we have found clever ways to adapt to MapReduce to do all of this. It really is a Swiss Army knife. It handles everything. Then, this went on for a number of years at Google. I was on the team for, I guess, about a year when this happened. And then we actually sort of had to put our money where our mouth was. Okay? In early 2011, you may or may not recall, Gmail had an outage, the worst kind. Not, we'll be back soon. Like, oops, where's my account? Okay, not a great thing to find. I remember at 10:31 p.m. on a Sunday, my phone, the pager app on my phone went off with the words, holy crap, and a phone number. And I turned to my wife and said, this can't be good news. I doubt it. She was like, maybe someone's calling to say hi. I'm like, I'm going to bet not. Sure enough, not. So there was a whole series of bugs and mishaps that you can read about what was made public and what wasn't. But this was a software bug, plain and simple. We have unit tests, we have system tests, we have integration tests. Nonetheless, 1 in 8 billion bugs gets through, and of course, this was the one. And the best part is it was in the layer where replication happens. So as I said, I've got 2 other copies. Yes. And you have 3 identical empty files. You work with that. So we finally had to go to tape And luckily for me, revealed to the world that we use tape. Because until then, I couldn't really tell people what I did for a living. So what do? Oh, I like eat lunch. Like, I could finally say, yes, I do that. So we had to restore from tape. And it's a massive job. And this is where I mentioned that the meaning of a short time or immediately is relative to the scale, right? Like if you were to say, get me back that gigabyte instantly means milliseconds or seconds. If you say, get me back those 200,000 inboxes of several gig each, probably you're looking at more than a few hundred milliseconds at this point. And we'll go into the details of it in a little bit. But we decided to restore from tape. I woke up a couple of my colleagues in Europe because it was daytime for them and it was nighttime for me. And again, I know my limits. Like, you know what? I'm probably stupider than they are, like all the time, but especially now when it's midnight and they're getting up anyway. Okay, so the teams are sharded for this reason. We got on it. It took some number of days that we'll look at more detail in a little bit. We recovered it. We restored the user data, and done. Okay, and it didn't take order of weeks or months. It took order of single-digit days, which I was really happy about. I mean, there have been, and I'm not going to go into unbecoming specifics about other companies, but you can look. There have been cases where providers of email systems have lost data. One in particular I'm thinking of took a month to realize they couldn't get it back. And 28 days later said, oh, for the last month we've been saying wait another day. Turns out, nah. And then a month after that, they actually got it back, but nobody cared because everybody had found a new email provider by then. So we don't want that. Okay, we don't want to be those guys and gals. And we got it back in order of single-digit days, which is not great. And we've actually taken steps to make sure it would happen a lot faster this time. But again, we got it back and we had our expectations in line. How do we handle this kind of thing, like Gmail, where the data's everywhere? Okay, we don't have backups. Like, for example, let's say we had a New York data center. Oh, my backups are in New York. That's really bad because then if one data center grows and shrinks, the backup capacity has to grow and shrink with it. And that just doesn't work well. We view our backup system as this enormous global thing, right? This huge, meta system, or this huge organism, okay? It's worldwide. And we can move things around, okay? When you back up, you might back up to some other place entirely. The only thing, obviously, is once something's on a tape or on a physical, not a physical drive, when it's on a tape, the restore has to happen there, because tapes are not magic, right? They're not intangible. But until it makes the tape, you might say, my data's in New York. Oh, but your backup's in Oregon. Why? Because that's where we had available capacity, it had location, isolation, et cetera, et cetera. And it's really one big happy backup system globally. And the end users don't really know that. We never tell any client service, unless there's some sort of regulatory requirement, we don't tell them your backups will be in New York. We tell them, you said you needed location isolation. With all due respect, please shut up and leave us to our jobs, okay? And where is it? I couldn't tell you, to be honest. Like, that's the system's job. Okay, that's a job for robots to do, not me. And this works really well because it lets us move capacity around and not worry about, like, if I move physical disk around, I have to move tape drives around with it. As long as the global capacity is good, the network can support it, we're okay, and we can view this one huge pool of backup resources as just that. So now the details I mentioned earlier, the Gmail restore. Let me see, who wants to give me a complete swag, right? A crazy guess as to how much data is involved if you lose Gmail. You lose Gmail. How much data? What units are we talking about? Nobody? What? Well, not quite yottabytes. Okay, that was, in the Price is Right, you just lost because you can't go over. So, but yeah, I'm flattered, but no, it's not yottabytes. It's, it's on the order of many, many petabytes or, or approaching low exabytes of data, right? You've got to get this back somehow. Okay, tapes are finite in capacity, so that's a lot of tapes. Okay, we're faced with this challenge. Restore all that as quickly as possible. Okay, I'm not going to tell you the real numbers because if I did, like the microwave lasers on the roof would probably take care of me. But, let's talk about what we can say. So I read this fantastic, at the time, and I'm not being facetious, it was a fantastic analysis of what Google must be doing right now during the Gmail restore that they have publicized. And it wasn't perfectly accurate, but it had some reasonable premises, it had a logical methodology, and it wasn't insane. So I'm going to go with the numbers they said. Okay? They said we had 200,000 tapes to restore. Okay? So at the time, the industry standard was LTO4. Okay? And LTO4 tapes hold about, zero point 0.8 terabytes of data, and at 120 megabytes per second, they take roughly 2 hours to read. Okay, so if you take the amount of data we're saying Gmail must have, and you figure out how many, at 2 hours per tape, capacity of tape, that's this many drive hours. If you want it back in an hour, well, that's impossible because the whole tape takes 2 hours. Okay, let's say I want it back in 2 hours. So I've got 200,000 tape drives at work at once. All right, show of hands. Who thinks we actually have 200,000 tape drives? Even worldwide. Who thinks we have 200,000 tape drives? Really? You're right. Yes. Okay. Thank you for being sane. Yes, we do not have. I'll say this: we do not have 200,000 tape drives. Okay. We have some number. It's not that. So let's say I had one drive. No problem. In 16.67 thousand days, I'll have it back. Probably you've moved on to some other email system. Probably the human race has moved on to some other planet by then. Okay. Not happening. All right. So there's a balance, right? Now, we restored the data from tape in less than 2 days, which I was really proud of. So if you do some arithmetic, this tells you that it would have taken 8,000 drives to get it back nonstop, doing nothing but. 8,000 drives are required to do this with the numbers I've given earlier. Okay, typical tape libraries that are out there from Oracle and IBM and Spectralogic and Quantum. These things hold, several dozen drives, like between 50 and 100 drives. So that means if you take the number of drives we're talking about by the capacity of a library, you must have had 100 libraries, 100 large tape libraries, okay, doing nothing else but restoring Gmail, okay, for over a day. If you have them in one location, okay, if you look at how many kilowatts or megawatts of power each library takes, I don't know, like, I'm sorry, you with the glasses? Sorry, what's your question?
How much power is that?
1.21 gigawatts, I believe.
Great Scott!
Yes, we do not have enough power to charge a flux capacitor in one room. If we did, we'd be going. If we did, okay, that kid who beat me up in high school would never have happened. So yes, I promise we don't have that much power. So how did we handle this, right? Okay. I can tell you this. We did not have 1.21 gigawatts worth of power in one place. The tapes were all over. Also, it's a mistake to think that we actually had to restore 200,000 tapes worth of data to get that much content back, right? There's compression, there's checksums, there's also prioritized restores. Do you actually need all of your archived folders back as quickly as you need your current inbox and your sent mail? Okay, if I tell you, and there's, accounts that have not been touched in a month, you know what? I'm going to give them the extra day. On the other hand, I read my mail every 2 hours. You get your stuff back now, miss. Okay, that's easy. All right, so there's prioritization of the restore effort. Okay, there's, different data compression and checksumming. Okay, it wasn't as much data as they thought in the end to get that much content. And we didn't take, it was not 1.21 gigawatts in a room. And yeah, so that's a really rough segue into this slide. But one of the things that we learned from this was that we had to pay more attention to the restores. Until then, actually, we had thought backups were super important, and they are, but they're really only a tax you pay for the luxury of a restore. So we started thinking, okay, how can we optimize the restores? And I'll tell you this, while I can't give you exact numbers, can't and won't give you exact numbers, it would not take us nearly that long to do it again today. Okay, and wouldn't be fraught with that much human effort. It really was a learning exercise, and we got through it, but we learned a lot, and we've improved things, and now we really only worry about the restore. We view the backups as some known steady state thing. If I tell you you've got to hold on to your source data for 2 days because that's how long it takes us to back it up, okay, you can plan for that. As long as I can promise you, when you need the restore, it's there, my friend. Okay, so the backups are, like I said, the steady state. It's a tax you pay for the thing you really want, which is data availability. On the other hand, when a restore happens, like the Gmail restore, we need to know that we can service that now and quickly. So we've adapted things a lot towards that. We may not make the most efficient use of media, actually, anymore, because it turns out that taking 2 hours to read a tape is really bad. Increase the parallelism. How? Well, maybe only write half a tape. You have twice as many tapes. You can read them all in parallel. I can get the data back in half the time if I have twice as many drives, right? Because if I fill up a tape, I can't take the tape, break it in the middle, say to 2 drives, here, you take half, you take half. Now then, if I write it to 2 tapes, side A and side B, I can put that into 2 drives, read them in parallel. So we do that kind of optimization now towards fast, reliable restores. We also have to look at the fact that a restore is a non-maskable interrupt. So one of the reasons we tell people your backups really don't consider them done until we say they're done. When a restore comes in, that trumps everything. Okay? Restores are suspended. Get the backup restore. Get the restore done now. That's another lesson we've learned. It's a restore system, not a backup system. Okay? Restores win. Okay? Also, restores have to win another reason. Backups, as I mentioned earlier, are portable. If I say back up your data from New York and it goes to Chicago, what do you care? And then if your tape is in Chicago, the restore must happen in Chicago, right? Unless I'm going to FedEx the tape over to New York somehow, magically. Call the flash, okay? So we've learned how to balance these things. That we wish backups would go away. We want a restore system. So quickly jumping to a summary, okay? We have found also the more data we have, the more important it is to keep it. Odd but true, right? There's no economy of scale here. The larger things are, the more important they are as a rule. Back in the day when it was, web search, right? In 2001, what was Google? It was people typing. It was a plain white page, right? The text box. People would type in Britney Spears and see, the result of the search. Okay. Now Google is Gmail. It's stuff held in Drive, stuff held in Vault, right? Docs. Okay. It's larger and more important, which kind of stinks. Okay, so now the backups are both harder and more important. So we've had to keep the efficiency, improving. Utilization and efficiency have to skyrocket because we can't have it, as I said earlier, twice as much data or 100 times the data can't require 100 times the staff power and machine resources. It won't scale, right? The universe is finite. So we've had to improve utilization and efficiency a lot, okay? Something else that's paid off enormously is having good infrastructure. Things like MapReduce, I guarantee when Jeff and Sanjay wrote MapReduce, they never thought it would be used for backups, okay? But it's really good, bless you. It's really good to have general purpose Swiss Army knives, right? Like someone looked, and I really give a lot of credit. The guy who wrote our first backup system said, you know what? I'll bet I could write a MapReduce to do that. I hope that guy got a really, really good bonus that year because that's awesome thinking, right? That's visionary. And it's important to invest in infrastructure. If we didn't have MapReduce, it would have been there for this, guy or gal to think of. So in a very short, and this kind of thing has paid off for us enormously. When I joined tech infrastructure, who was responsible for this, we had, 1/5 or 1/6 maybe the number of backup sites and the capacity that we did. And maybe we doubled the staff. We certainly didn't increase. We certainly didn't quintuple it or sextuple it. We've had to increase, but it's not linear at all. But scaling is really important, and you can't have any piece of it, okay, that doesn't scale. You can't say I'm going to be able to deploy more tape drives, okay. But what about operations staff? Oh, yeah, I have to scale that up. Well, I'll just hire twice as many people. Okay, do you have twice as many parking lots? Do you have twice as much space in the cafeteria? Do you have twice as much salary to give out? That last part is probably not the problem, actually. It's probably more likely the parking spots and the restrooms. I mean, everything has to scale up, okay? Because if there's one single point, one bottleneck, you're going to hit it and it'll stop you. So even the processes, like I mentioned, our shipping processes had to scale, had to be more efficient, and they are. And we don't take anything for granted. One thing that's great, one of our big SRE mantras is hope is not a strategy. Okay, this will not get you through it. This will not get you through it. Sacrificing a goat to Minerva will not get you through it. Okay, if you don't try it, it doesn't work. That's it. When you start a service backing up at Google, force is not the right word, but we require that they restore it and load it back into a serving system and test it. Why? Because it's not going to say, oh, look, I'm pretty sure it made it this far. No, you know what? Take it the rest of the way, honestly. Oh, who knew that would break? Indeed, who knew? The morgues are full of people who knew that they could make that yellow light before it turned red. Okay? So until you get to the end, we don't consider it proven at all. And this has paid off enormously. We have found failures at the point where what could go wrong, who knew, right? And it did. So unless it's gone through an experiment all the way to completion, we don't consider it. If there's anything unknown, we consider it a failure. That's it. And towards that, I'm going to put a plug in for DIRT, one of my pet projects. So DIRT is something we publicized for the first time last year. It's been going a while. Disaster recovery testing. Every N months at Google, where N is something less than 10 billion, okay, and more than 0, we have a disaster. It might be that Martians attack California. It might be Lex Luthor finally is sick of all of us and destroys the Northeast. It might be cosmic rays. It might be solar flares. It might be the IRS. Some disaster happens, okay, on those one of those cosmic orders of magnitude. And the rest of the company has to see how will we continue operations without California, North America, tax returns, whatever it is, okay? And we simulate this to every level, down to the point where if you try to contact your teammate in Mountain View to say, hey, can you cover, your response will be, I'm underwater, glub, glub, look somewhere else. Okay, or I'm lying under a building, God forbid, right? But you have to see how will the company survive and continue operations without that being whatever's taken by the disaster. We don't know what the disaster will be. We find out when it happens. You'll come in one day, hey, I can't log on. Oops, I guess dirt has started. Okay, and you've got to learn to adapt. And this finds enormous holes in our infrastructure, in physical security, in something. Imagine something like we've got a data center with one road leading to it, and we have trucks filled with fuel trying to bring fuel for the generators. That road is off. Gee, better have another road, and another supplier for diesel fuel for your generators. That level through simple software changes, like you should run in 2 cells that are not in any way bound to each other. So we do this every year. It pays off enormously. It's a huge boon to the caffeine industry. I'm sure the local coffee suppliers love when we do this. They don't know why, but every year around that time, sales spike. And it teaches us a lot every year. And what's amazingly is after several years of doing this, we still find new kinds of problems every year. Because apparently the one thing that is infinite is, trouble, right? There will always be some new problem to encounter. Really what's happening is you got through last year's problem, there's another one waiting for you just beyond the horizon. Like so. Disaster. Wow, it looks like I really did something. Okay, so I'll just carry it. And yes, there's no backup, but luckily I'm an engineer. I can clip things. So with that pretty much is what I had planned to talk about, and luckily, because that is my last slide. And I'm going to open up to any questions. Please come up to a mic, or, I think this is the only mic, right? Yeah. Good.
Hi.
Hi.
Thanks. I have no
You're welcome.
shortage of questions.
Start.
Since you take hashes of the files, does that mean that you dedupe the files and only make a smaller number of copies than required, or a single copy if you already have it?
Is this microphone on?
Apparently not.
Hold on, I can fix this.
Let's do that again.
Let's try that.
Oh, power.
Right. My question was, do you dedupe the files or record only one copy of a file that you already have an adequate number of copies of?
There's not a hard set answer for that, and I'll point out why. Sometimes deduping is, the process needed to dedupe is more expensive than keeping multiple copies. For example, I've got a copy in Oregon and a copy in Belgium, and they're really large. Well, you know what? For me to run the checksumming and the comparison, you know what? Honestly, just put them on tape.
That's why I said an adequately backed up copy.
Yes. On the other hand, there are some, like for example, probably things like Google Play Music have this. You can't dedupe. Like, sorry, the law says you may not. I am not a lawyer. Don't take it up with me.
Back up, but you can't dedupe.
Huh?
You can back up, but you can't dedupe.
You cannot dedupe. You cannot say your file and your file, same thing. If he bought a copy and he bought a copy, I want to see 2 copies. I'm the recording industry. So I mean, I'm not sure that's exactly a use case, but those sorts of things happen. But yeah, there's a balance, right? Sometimes it's a matter of deduping. Sometimes it's just back up 1,000 times.
But my question is, what do you do?
It's
Sometimes
a case-by-case basis.
Sometimes you dedupe.
It's a whole spectrum.
Okay.
Right? There's deduping by region, deduping by
Okay.
time.
And when you have large copies of things which you must maintain an integral copy of, and they're changing out from under you, how do you back them up without? Do you front run the blocks or?
Sorry, you just crashed my parser.
You have, let's say you have a 10 gigabyte database and you want an integral copy of it in the backups, but it's being written while you're backing it up.
Oh, okay, got it.
Maintain an integral copy. How do you back up an integral copy?
We don't.
Okay.
We look at all the mutations applied, and we take basically a low watermark. We say, you know what? I know that all the updates as of this time were there. So we say, your backup is good as of then. There may be some trailing things after, but we're not guaranteeing. We are guaranteeing that as of now, it has integrity, and you will have to handle that somehow.
I don't understand. If you have a 10 gigabyte database and you back it up linearly, at some point you will come upon a point where someone will want to write something that you haven't yet backed up. Do you defer the write? Do you keep a transaction log? I mean, there are sort of standard ways of doing that. How do you prevent the first half from being integral and the second half from being inconsistent with the first half?
No, there may be inconsistency.
Oh, there may be inconsistency.
We guarantee that there is consistency as of this point in time.
Oh, I see. So the
And
first half
past
could
that,
be integral.
Ask Heisenberg. I have no idea. But as of then, I can guarantee that everything's cool.
You may never have an integral copy.
Oh, there probably isn't.
In that case.
No, you can say this snapshot of it is good as of then.
It's not a complete.
Right, the whole thing is not,
okay.
But I can guarantee that anything as of then is. Anything after that, you're on your own.
Hi, you mentioned having backups in different media like hard disk and tape.
Cuneiform.
Yeah, Adobe tablets. And you may recall that there was a issue in South Korea a while ago where suddenly it was the supply of hard disks suddenly dropped because there was some manufacturing issue. Do you have any supply chain management redundancy strategies?
Yes. Sorry, I don't know that I can say more than that, but I can say yes.
Okay.
We do have some supply chain redundancy strategy.
Okay. And then one other question was, do you have a Amazon Web Service Chaos Monkey-like strategy for your backup systems in general for testing them? So, kind of similar to Dirt, but only for backups.
You didn't quite crash it, but my parser is having trouble. Can you try again?
Amazon Web Services has this piece of software called Chaos Monkey that randomly kills processes, and that helps them create redundant systems.
Gotcha.
Do you have something like that?
We do not go around sniping our systems. We find that failures occur quite fine on their own. So no, we don't actively do that. But that's where I mentioned that we monitor the error rate. In effect, we know there are these failures. All right, failures happen at n. As long as it's at n, it's cool. There was a change in the failure rate. That is actually a failure. It's a derivative, let's say, of failures. Is actually the failure. And the systems are expected to handle the constant failure rate.
What if it goes down?
That's a big change in the failure rate.
If the rate goes down, is that okay, though?
If what goes down, sorry?
The failure rate.
Sorry. Oh, yeah. No, that's still a problem.
Why is it a problem?
It shouldn't have changed. That's it. So we will look and say, you know what? It turns out that zero failure, like a reduction in failure, means that half the nodes aren't reporting anything. Like that kind of thing happens. So we look at any change as bad.
Okay, thank you.
You're welcome.
Hi. 2 questions. One is simple, kind of yes, no. So I have this very important cat video that I made yesterday. Is that backed up?
Sorry?
The important cat video that I made yesterday. Is that backed up? Do you back up YouTube?
Do you want me to check?
Yes, no. Yes, no. Okay.
I'm going to say yes.
Because you
mentioned I don't know the specific cat, but I'm going to say yes.
That's a big data set.
Yeah. Oh, no, cats. No, we take cats on YouTube very seriously.
All right.
My mother knows that Jan Cat loves her. No, we hold on to those cats.
Okay. So a second question. So I figure out your shipping schedule, and I steal one of the trucks.
You assume that we actually ship things through this through these three physical dimensions using something as primitive as trucks.
You said so. Twice, actually.
Oh, that was just a
It's a
silk
physical
screen. That was a
security
silk
and
screen.
trucks. Yeah.
Well, no. I mean, the stuff is shipped around, and if that were to happen, both departure and arrival are logged and compared. And if there's a failure in arrival, we know about it. And until then, until arrival has been logged, we don't consider the data to be backed up.
Okay.
Like, it actually has to
I'm
get
I'm
where
more
it's
concerned
going.
about the tapes themselves.
Oh,
My data.
I promise you that we have this magical thing called encryption that, despite what government propaganda would have you believe, works really, really well if you use it properly.
Okay. All right. Thank you.
Yeah, no, it's your cats are encrypted and safe. You're welcome.
Hi. Thanks for
They
the
look
talk.
like dogs on the tapes. Yes.
Thanks for the talk. It was really interesting.
Thank
so
you.
I have 3 quick questions.
Go ahead.
The first one is something that I always wondered is how many copies of a single email in my Gmail inbox they exist in the world.
Oh, I don't know.
Is it like 3 or 10 or?
I don't know.
Okay.
Honestly, like, I know it's enough that there's redundancy guaranteed and that it's safe, but like I said, that's not a human's job to know. Like, somebody in Gmail set the parameters, and some system said, yeah, that's good, and
Okay.
sorry.
The second one is related to something that I read recently. Twitter is gonna.
Well, I can say this. I can say more than one and less than 10,000.
Okay.
Okay.
That's not very.
One with the NSA.
Okay, that doesn't help.
They wish.
It's not very helpful response, but it's fine.
No, I really don't know. Sorry.
So I was reading about Twitter is gonna file an IPO, and something that I read on an article by someone from Wall Street said that actually Twitter is not that impressive because you have these bank systems that they never fail, like ever, and then
Right, never ever.
that's what these
Keep
guys
believing
say.
in that.
And then he said, like, well, actually, Twitter, Google, these things, they sometimes fail and they lose data, so they're not actually that reliable. What do you think about that?
Okay, I'm going to give you a great analogy. You with the glasses. Pinch my arm really hard. Go ahead, really, I can take it. No, like really with your nails. Okay, thanks. Yeah, so you see that? He probably killed, like, what, 20,000 cells? I'm here. Like, yes, Google stuff fails all the time. It's crap, okay? But, the same way these cells are, right? So we don't even dream that there are things that don't die. We plan for it. So yes, machines die all the time. Redundancy is the answer. Right now, I really hope there are other cells kicking in and repair systems are at work. I really hope, please, okay? And that's how our systems are built, a biological model, let's call it.
But what I
We
think
expect things to die.
I think at the beginning I read that you also worked on something related to Wall Street. My question was also, is Google worse than Wall Street system? Or
What does that mean, worse than? I'm sorry, I don't understand.
less reliable?
I actually would say quite the opposite. So at one firm I worked at that I, again, will not name, they bought the best, right? And now, let me say, I love Sun Equipment. Okay, before they were Oracle, I really loved the company too. Okay, and they've got miraculous machines, right? You can, like, open it up, pull out RAM, replace a daughter board with a processor, and the thing stays up and running. It's incredible. But when that asteroid comes down, that is not going to save you. Okay, so yes, they have better machines than we do. But nonetheless, if I can afford to put machines in 50 locations, and the machines are half as reliable, I've got 25 times the reliability, and I protect it from asteroids. So the overall effect is our stuff is much more robust. Yes, any individual piece is, like I said the word before, right? It's crap, okay? But we're not looking, like this cell was crap, but luckily I'm more than that. And likewise, our entire system is incredibly robust because there's just so much of it.
Okay, and my last question is, could you expand on MapReduce? I don't really know how it works.
So MapReduce is something he's probably better equipped, or she is, or that guy there. I don't really know MapReduce all that well. I've used it, but I don't know it that well. But you can Google it. There are white papers on it. It's publicly known. There are open source implementations of it. But it's basically a distributed processing framework that gives you two things to do. You can split up your data, and you can put your data back together. And MapReduce does all the semaphores, handles race conditions, handles locking, okay, all for you, because that's the stuff that none of us really know how to get right. And yeah, but if you Google it, there's like a really, really good white paper on it from several years ago.
Thank you.
You're welcome. Hi.
Alex, and
Alex.
thanks very much for the nice presentation.
Thank you.
I was glad to hear you talked about 100% guaranteed data backup, and not just backup, but also recoverability. I think it's probably same as the industry term, the RPO, recovery point objective equals 0.
Yeah.
First question is, in 2001 incident, 2011 incident, were you able to get 100% of data?
Yes.
Uh,
Now, availability is different from recoverability.
Right, yes.
It wasn't all there in the first day. It was, as I mentioned, it wasn't all there in the second day, but it was all there, and availability varied. But at the end of the period, it was all back.
So how could you get 100% of data when your replication failed because of this corruption or some data corruption? But the tape is a point of time copy, right?
Yes.
So how
So
could you?
what happened is, okay, without going into things that I can't or shouldn't, or I'm not sure if I should or not. Okay, the data is constantly being backed up, right? So let's say we have the data as of, I don't know, 9 p.m., right? And let's say the corruption started at 8 p.m. but hadn't made it to tapes yet, okay? And we cease the corruption, we fall back, to an early version of software that doesn't have the bug. Pardon me. So at some point, at 11, at some point in the stack, all the data is there. There's stuff on tape, there's stuff being replicated, there's stuff in the front ends still not digested as logs. So we're able to reconstruct all of that. And there was overlap. So, look, the logs had till then. The backups had till then. This other layer in between had that much data. So there was, I don't know how else to say it, but I'm not articulating this well. But there was overlap, and that was built into it. The idea was, you don't take it out of this stack until n hours after it's on this layer. Why? Just because. And we discovered the because really paid off.
So you keep the delta between those copies.
Yes, there's a large overlap between the strata. I guess is the right way to say it.
I just have one more question.
Sure.
The speed of these data increasing nowadays is gonna be double and triple in certain years. Who knows, right?
Oh yeah. Yes.
Do you think there is a need for new medium rather than tape to support that backup?
There's got to be something. Well, I would have said yes. Let me think about this. What days am I thinking about?
My question, yeah.
So in the mid-90s, I guess, when it was 250 gig on a cartridge, and those were huge, and then there were things like, zip disks, right?
Right.
Gigabytes. I would have said yes. But now I'm always really surprised at how either the laws of physics, the laws of mechanics, or the ingenuity of tape vendors. I mean, the capacity is going with Moore's law pretty well. So, LTO4 was 800 gig. LTO5 is almost 5 T. LTO6 tapes are 2.4 T, I think, or 2.3 T. So yeah, they're climbing. They don't the industry has called their bluff. When they said this is as good as it can get, turns out it wasn't. So it just keeps increasing. At some point, yes. But also you're going to want more and more random access media, not things like tape.
Google looking at something or doing research for that?
I can say the word yes.
Okay.
Yeah.
Good enough. Thank you.
You're welcome.
For your talk.
Thank you.
So from what I understand, Google owns its own data centers. But there are many other companies that cannot afford to have their own data centers. So many companies operate in the cloud and they store their data in the cloud. So based on your experience, do you have any strategies for backing up and restoring from the cloud? Data that is stored on the cloud?
I need a tighter definition of cloud.
So, for example, someone operating completely using Amazon Web Services.
I would hope that then Amazon provides, they do, right? A fine backup strategy. Not as good as mine, I want to think, but, I'm just a little biased. But,
Are there any other strategies that companies that operate completely in the cloud should,
yes.
consider?
Just general purpose strategies. I think the biggest thing that people don't do that they can, no matter what your resource, you can do a few things, right? Consider the dimensions that you have to, that you can move sliders around on, right? There's location, okay? There's software, and I'll view software as vertical and location as horizontal, right? So I want to cover everything. So that would mean I want a copy in, which one did I say? Yeah, in every location, and in every location in different software layers in the software stack. And you can do that by having like, if you even just have like VMs from some provider, like, I don't know who does that these days, but some VM provider, provider X, right? And they say, our data centers are in Atlanta. Provider Y says, our data centers are in, where's far away from Atlanta? Northern California. Okay, fine, there, I've got location. We store stuff on EMC SAN devices. We store stuff on some other thing. Okay, fine, now I'm isolated against vendor bugs. And just, doing that way, here's a little research and, I don't want to say hard work, but, plotting it out, on a big map, basically. And just doing that, I think, is a huge payoff. I mean, it's what we're doing, really.
So increasing the redundancy factor.
Redundancy, yes, but redundancy in different things. Most people think of redundancy only in location. And that's my point. It has to be redundancy in these different redundant software stacks and redundant locations, the product of those, at least. And also, Alex, yeah. What he said, right? Which was, he said something, I'm going to get it back in a second. Loading. Okay, yes. Redundancy even in time. It was here in the stack, migrating to here. You know what? Have it in both places for a while. Like, don't just let it migrate through my stack. Okay, don't make the stacks like this. Make them like that so there's redundancy. Why? Because if I lose this and this, oh, look, I've got enough overlap that I've got everything. So yeah, location, like redundancy in time, location, and software.
Thank you.
You're welcome. Hi again.
Hi. So if I understand your description of the stacks, it sounds as if every version of every file will end up on tape somewhere, sometime.
Not necessarily, because there are some things that we don't. Because it turns out that in the time it would take to get it back from tape, I could reconstruct the data.
Huh.
You know what? Then don't put it on tape. I mean, then don't bother me.
Do you ever run tape in faster than linear speed? In other words, faster than reading the tape or writing the tape by using the fast forwarding or seek to a place?
Where the drives allow. We do what the drives allow, yes.
Okay.
Yeah.
And how are you going to change the encryption key if you need to? With all of these tapes and all of these drives, you have a gigantic key distribution problem.
Yes, we do.
Have you worried about that in your dirt?
We have, and it's been solved.
Oh, wonderful.
To our satisfaction, anyway. Sorry, I can say yes, though. And I'll say one more thing towards that, which is actually, think about this, a problem where a user says something like, I want my stuff deleted. Yes. Okay, it's on a tape with a billion other things. I'm not recalling that tape and rewriting it just for you. I mean, I love you like a brother, but I'm not doing that, okay? So what do? Encryption. Yes. Yeah, so we have our key management system is really good for reasons other than what you said. I mean, it's one of those Swiss Army knives that keeps paying off in like the ways I just described. Anything else? Going once and twice.
All right, so there's all these different layers of this that are all coming together. How do you coordinate all that?
Very well, thank you. Can you give me like a more specific?
I mean, between maintaining the data center, coming up with all the different algorithms for caching different places, things like that. I mean, are there like a few key people who know how everything fits together?
There are people. All right, so this is a big problem I had at first when I came to Google. So before I came to Google, I was, and this is not a statement about me, so maybe as much as the company I kept, but I was the smartest kid in the room. And then when I came to Google, I was an idiot, okay? And a big problem with working here was you have to accept that. You are an idiot, like all the other idiots around you, okay? Because it's just so big. Okay, so what we're really good at is trusting our colleagues and sharding. Like, I know my part of the stack. I understand there is someone who knows about that part of the stack. I trust her to do her job. She hopefully trusts me to do mine. The interfaces are really well defined. And there's lots of tests, but at every point of interaction. And there are people who maybe have the meta picture, but I would pretty much say no one knows all of it in depth, right? People have broad views, people have deep, vertical slices, but no one's got it all. It's just not possible. Hi.
Hi. So I wanted to ask how much effort is required to deal with like local regulation. So you described your ability to back up in this very abstract way. Like, we'll just let the system decide whether it goes into Atlanta or London or Tokyo or wherever. But obviously now we're sort of living in a world where governments are saying, hey, you can't do that, or this needs to be deleted, or this needs to be encrypted in a certain way, or we don't want our user data to leave the country.
Yes, this happens a lot. And this is something that I know is publicly known, so I'm going to be bold for a change. Well, no, I'm bold all the time, actually. But I'll say this. So we have actually apps, we won some number of years and months ago the contract to do a lot of like, let's call it IT systems for the U.S. government. A lot of government agencies are on Gmail, Gmail for enterprise, in fact, but the enterprise is the U.S. government. And that was a big thing, like the data may not leave the country, period. If we say it's in the state of Oregon, it's in the state of Oregon. And we've had to go back and retrofit this into a lot of systems, but it was a massive effort. Luckily, the stuff was all Thank you. That blinking did work. Thanks. We've had to go back and build that in. Luckily, all the systems were modular enough. It wasn't a terrible pain because of the well-defined interfaces I stressed so much in response to, I think it was Brad's question a few minutes ago. And yeah, it had to be done. There are two kinds, right? There's whitelisting and blacklisting. Our data must stay here, and our data must not be there. And most of our systems and infrastructure do that now. And what we've tried to do is push that stuff down as far as possible, so the greatest possible benefit. So we don't have 100 services at Google who know how to isolate their data. We know how to say on the storage layer, it must have these white or blacklists associated with it. And all the services write to it, just say, I need profile X or Y, and hopefully the right kind of magic happens. But yeah, it's a huge problem, and we have had to deal with it, and we have.
Could you go into a little more detail about using MapReduce for the backup and restore task? Just sort of like what sort of parts of the backup and restore apply to it?
Oh, sure. Let's say I've got, do you know what Bigtable is?
Yeah.
Okay, so Bigtable is like our database system, quotes around database. It's a big hash, big hash map on disk, basically, and in memory. So if I've got this enormous Bigtable, and remember the first syllable of Bigtable, right? I'm going to read this serially. Okay, that'll take 5 years. Okay, on the other hand, I can shard it and say, you know what? I'm going to take the key distribution, slice it up into 5,000 roughly equidistant slices, and give 5,000 workers, okay, you seek ahead to your position, you back that up.
Sure.
Okay, and then on the restore, likewise, okay, I'm going to start reading. Okay, well, I've put this onto 20 tapes. Okay, give me 20 workers. Okay, what they're each doing is, reading a tape, sending it off to N, let's say 5,000 workers up near Bigtable, whose job it is to get some, get some compressed protobuf, unpack it, stick it into the Bigtable at the right key range.
Okay.
And it's just that. It's a question of sharding into as small units as possible.
Okay, so it's just a matter of, I guess, creating that distribution.
Yeah,
So,
and that's what MapReduce is really, really good at.
right.
Yeah, that's its only thing it's really good at, but that's enough. Yeah.
It's just getting it to be that simple, or getting it to simplify it to that point is
Yeah.
really hard.
Yeah, oh no, I agree. It's very hard, and that's when I fell in love with MapReduce. I was like, wow, I just wrote that in an afternoon.
Right.
Yeah.
And I guess what's roughly the scale? I mean, you said for Gmail it's on exabyte. I mean, for all of the data that Google's backing up, is that also in the exabyte or
It's not yottabytes. It's certainly more than terabytes, and yeah, there's a whole spectrum there. Yeah.
Including all the pedophiles?
I can't answer that.
Okay. Thank you.
You're welcome. And I'll give one more round for questions. Going thrice. All right, sold. Thank you all. Thank you.